Hi, so my name is Ben Kiesling, and I'm going to be talking to you guys today about my project, which is modeling a DC motor with a PID controller. So pictured here, we can see a DC motor on the left and how it rotates. On the right, we can see one of the many applications for DC motors. It's a little portable toy, but we can also see DC motors used in a wide variety of applications, such as robotics, household appliances, power tools, and some automotive uses. These motors are used very widely because of their variable speeds and their high starting torque. The stator is the stationary part of the DC motor. It's made up of a permanent magnet. The magnet creates a magnetic field that is going to interact with the rotor coils once a current is running through the rotor coils. The rotor or armature is the rotating part of the motor. It's made up of armature windings that are connected to the brushes and commutator rings that power the motor. Just as I said, the commutator and brushes are what carry the current from the DC battery into the rotor. Now, once a current is applied to the rotor, Lorentz law is going to take effect and the motor is going to start rotating. All right, so here you can see our transfer function for the DC motor. As it's in the bottom right as P motor, but it's made up of all these variables. Let me tell you what they are. J is our moment of inertia for the rotor. B is the viscous friction constant. Ke is the electromotive force constant. Kt is the motor torque constant. Now we can see in my transfer function, we just use K. And that's because Kt and Ke are the same value. Also, R is the resistance and L is the inductance of the motor. Here is the control system that will be implemented in my model. We can see it's an open loop response that uses a controller and a plant. Now the plant is the transfer function that I previously described, and we're going to go into more detail about how the controller was designed. But first, let's talk about my design requirements. Now, what I required for this project was less than 2% overshoot of my final value, which is 1. Less than 1% steady state error, and less than 0.5 seconds settling time. Alright, so we can see here that I've implemented a proportional controller. Now, in the end, I want to use a PID controller. A PID controller is made up of 3 main parts, P, I, and D. P stands for proportional, I stands for integral, and D stands for differential. So in this controller, we're only using proportional response. And we can see that in our line where we find C. Now C is the controller, and in this instance, we're only using a value for Kp. Now, once we use the feedback function to find our final system response and graph it, we can see some of our design requirements aren't met. Now for overshoot, we're looking for 2%. Now here we have 24%. Also, we can see that our final value, instead of 1, is going to be around 0.9. So this controller will not work. Next, we implemented a PI controller. Now a PI controller is adding the integral part, which should eventually lead to less steady state error. Now we see though the problem with this one is that our settling time is way too high. We have 16-second settling time. Also, our overshoot is much higher than what we would desire. Next, we'll implement a PD controller, just to kind of see what it does. Now we see with the PD controller, the rise time is much less. So hopefully with a PD, or the differential response, should cause our settling time to decrease. And we see that it does. Our settling time does decrease. But we do see that our final value is also, once again, not 1. So our error is going to be too large. So next what we did was create a PID controller. And what we have to do in creating a PID controller is tune it. So in order to do that, you have to kind of play around with the values and find what you're finally going to want to use. So these were my initial values. I used 75 for Kp, 1 for Ki, and 1 for Kd. And doing this, I saw that my settling time was decreased. It still wasn't fast enough at 0.664. And also, my steady state error wasn't going to be good enough. But my overshoot was going to be about right if we end up at 1. And here's the long-term response. We see that over time, it would come up to 1, but we needed to come up to 1 almost immediately. Now here's the final PID design. For this design, we implemented a value of 100 for Kp, 200 for Ki, and 10 for Kd. Now what we can see is our rise time for this is 0.1324, which is less than the 2 second, or less than the 0.5 seconds that we wanted. Next, we can see our percent overshoot is 1.02%, less than 2% once again. Finally, we can see that our value is staying very close to 1%, or 1, our final value, which means that our steady state error is going to be less than 1%, which is good. So, look at the long-term response. We can see that a PID controller is going to work much better than a P or a PI or a PD working by itself. Thank you guys so much for listening to me today. Have a great day.